The lifespan of a circuit breaker, specifically the number of times it can be turned on and off before potentially wearing out, is a complex question with no single, definitive answer. It depends heavily on several factors, primarily the type of breaker in question and the specific operating conditions it experiences. Circuit breakers are not designed to last indefinitely under constant switching. They are electromechanical devices, meaning they rely on both electrical and mechanical components to function. The mechanical components, such as the spring-loaded contacts and the tripping mechanism, are subject to wear and tear each time the breaker is operated. Repeatedly turning a breaker on and off introduces mechanical stress that can eventually lead to fatigue and failure. The electrical components, such as the contacts themselves, can also degrade over time due to arcing when the breaker opens under load. When a circuit breaker interrupts a current, especially a high current, an electrical arc is generated between the contacts as they separate. This arc causes erosion of the contact material, which can increase the contact resistance and eventually lead to overheating and failure. Some breakers are designed for more frequent switching and are built with more robust components to withstand the associated wear and tear. These breakers typically have higher endurance ratings and can withstand tens of thousands of on and off cycles under normal operating conditions. However, even these heavy-duty breakers have a finite lifespan and will eventually need to be replaced. Other breakers, particularly those used in residential applications, are designed for less frequent switching and have lower endurance ratings. These breakers may only be able to withstand a few thousand on and off cycles before their performance begins to degrade. The actual number of cycles a breaker can withstand will also depend on the operating conditions it experiences. Factors such as the magnitude of the current being interrupted, the frequency of switching, the ambient temperature, and the presence of corrosive substances can all affect the breaker's lifespan. For example, a breaker that is frequently used to interrupt high currents will experience more arcing and contact erosion, which will shorten its lifespan. Similarly, a breaker that is operated in a hot environment will experience accelerated degradation of its insulation and other materials. It is important to note that a breaker's lifespan is not simply a matter of the number of on and off cycles it has experienced. Other factors, such as the age of the breaker, its maintenance history, and its exposure to environmental factors, can also play a significant role. An older breaker that has been poorly maintained may be more likely to fail even if it has not been switched very often. Several standards and testing procedures are in place to ensure the reliability and safety of circuit breakers. These standards, such as those published by the National Electrical Manufacturers Association, or NEMA, and the Institute of Electrical and Electronics Engineers, or IEE, specify the performance requirements for different types of breakers and the testing methods used to verify compliance. Breakers are typically subjected to a variety of tests, including endurance tests, to determine their ability to withstand repeated switching operations. These tests are designed to simulate real-world operating conditions and to identify potential failure modes. The results of these tests are used to establish the breaker's endurance rating, which is typically expressed as the number of on and off cycles the breaker can withstand under specified conditions. While the endurance rating provides a useful indication of a breaker's expected lifespan, it is important to remember that it is only an estimate. The actual lifespan of a breaker in a particular application may be different depending on the specific operating conditions. To maximize the lifespan of circuit breakers and ensure their reliable operation, it is important to follow proper installation and maintenance practices. This includes selecting the appropriate type of breaker for the application, ensuring that the breaker is properly sized for the load it is protecting, and periodically inspecting and testing the breaker to identify any signs of wear or damage. Breakers should also be protected from excessive heat, moisture, and corrosive substances. If a breaker is found to be defective or nearing the end of its lifespan, it should be replaced immediately. Replacing breakers proactively, especially in critical applications, can help to prevent unexpected outages and ensure the safety of personnel and equipment. While it is difficult to predict the exact number of on and off cycles a circuit breaker can withstand, understanding the factors that affect its lifespan and following proper maintenance practices can help to maximize its reliability and prevent premature failure. Circuit breakers are essential components of electrical systems, providing protection against overloads and short circuits. Their reliable operation is crucial for ensuring the safety and efficiency of electrical equipment and systems. By understanding the factors that affect breaker lifespan and following proper maintenance practices, it is possible to extend their service life and prevent unexpected failures. One common misconception is that residential breakers are designed for frequent switching. In reality, they are primarily intended for overcurrent protection and occasional switching for maintenance or troubleshooting purposes. Repeatedly using a residential breaker as a switch can significantly reduce its lifespan. Industrial and commercial settings often utilize breakers designed for more frequent switching, such as those used in motor control circuits or lighting systems. These breakers are typically built with more robust components and have higher endurance ratings. However, even these breakers have a finite lifespan and should be inspected and maintained regularly. The environment in which a circuit breaker operates can also have a significant impact on its lifespan. High temperatures, humidity, and corrosive atmospheres can accelerate the degradation of the breaker's components and reduce its ability to withstand repeated switching operations. Proper ventilation and environmental controls can help to extend the lifespan of breakers in harsh environments. In addition to the number of on and off cycles, the magnitude of the current being interrupted can also affect the breaker's lifespan. Interrupting high currents generates more heat and arcing, which can accelerate the erosion of the breaker's contacts and reduce its ability to withstand future switching operations. In applications where breakers are frequently subjected to high currents, it may be necessary to use breakers with higher interrupting ratings or to implement other protective measures to reduce the stress on the breakers. Regular inspection and testing are essential for maintaining the reliability of circuit breakers and preventing premature failures. Visual inspections can help to identify signs of wear or damage, such as cracked insulation, loose connections, or corroded contacts. Electrical testing, such as insulation resistance testing and contact resistance testing, can help to detect hidden problems that may not be visible during a visual inspection. The results of these inspections and tests can be used to determine whether a breaker needs to be repaired or replaced. When replacing a circuit breaker, it is important to select a replacement breaker that is compatible with the existing electrical system and that meets the requirements of the application. The replacement breaker should have the same voltage rating, current rating, and interrupting rating as the original breaker. It should also be listed by a recognized testing laboratory, such as Underwriters Laboratories or UL, to ensure that it meets safety standards. Proper installation is also essential for ensuring the reliable operation of replacement breakers. The breaker should be installed by a qualified electrician who is familiar with the applicable electrical codes and standards. The electrician should also ensure that the breaker is properly connected to the electrical system and that all connections are tight and secure. In summary, the number of times a circuit breaker can be turned on and off before it is worn out depends on several factors, including the type of breaker, the operating conditions, and the maintenance practices. While it is difficult to predict the exact lifespan of a breaker, understanding these factors and following proper maintenance practices can help to maximize its reliability and prevent premature failures. Regularly inspecting and testing breakers, replacing them when necessary, and ensuring proper installation are all essential for maintaining the safety and efficiency of electrical systems. Keep in mind that certain types of circuit breakers, such as those used in ground fault circuit interrupters, or GFCIs, and arc fault circuit interrupters, or RFCIs, have additional testing requirements. These breakers should be tested monthly to ensure that they are functioning properly. The testing procedure typically involves pressing a test button on the breaker and verifying that the breaker trips. If the breaker does not trip when the test button is pressed, it should be replaced immediately. Circuit breakers are designed with different interrupting capacities. This refers to the maximum short circuit current that a breaker can safely interrupt. Using a breaker with an inadequate interrupting capacity can lead to catastrophic failure during a short circuit, posing a significant safety hazard. It's crucial to ensure the breaker's interrupting capacity matches or exceeds the potential fault current at its installation point. Consulting an electrical engineer for a short circuit study is recommended, particularly in commercial and industrial settings, to determine the available fault current. The proper coordination of circuit breakers is essential for selective tripping. This means that only the breaker closest to the fault should trip, minimizing disruption to the rest of the electrical system. Achieving selective tripping requires careful selection of breaker types and settings, and often involves the use of time current curves to coordinate the tripping characteristics of different breakers in the system. In some cases, using fuses in conjunction with circuit breakers can improve coordination and provide better protection. Fuses offer very fast interruption speeds for high fault currents, which can help to limit the let-through energy and reduce the stress on downstream breakers. The decision of how many cycles a breaker can withstand before failure is also related to the quality of its manufacturing. Higher quality breakers will have longer lifespans under the same conditions compared to lower quality, cheaper breakers. The cost of a quality circuit breaker upfront may save money in the long run because they will not need to be replaced as often. It is not uncommon to have a failure of a breaker because of a manufacturing defect or because it was not properly selected for the applied load and location. Consider the environment the breaker is in as well. A breaker in a very dirty or wet location may need to be in an enclosure to protect it from the elements. Another key thing to remember: the lifespan of a breaker is reduced significantly if it is constantly tripping. If a breaker is constantly tripping, that means that the load is excessive or there is a problem in the wiring. This needs to be fixed to prolong the life of the breaker. If there are multiple circuits feeding the load, try splitting it up. It could be that the load is just too much for a single breaker, but you will want to fix this rather than put in a bigger breaker. The breaker is tripping for a reason, and it is protecting the wiring and the equipment that is connected.